Hello and welcome to Technically Speaking, a podcast where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Aneeqa, and in this episode, I'm joined by Rwayda and Laura to talk about fire safety and materials used in fire safety. Rwayda, I know you have a background. Your PhD was in fire safety for buildings. So can you tell us a little bit about why you care about this topic?
So first I will start this with a question this time. So I would say, would you build a furnace out of timber?
Only if you wanted to burn the furnace at the same time as getting heat.
Yeah, so basically you just answered your own question about fire safety and why we are interested in it. So basically we need to use the appropriate material for a specific application. So if we need to burn that furnace, we will build it out of timber because that timber will be burned, or we can clad that with a material that is not flammable and we protect the furnace. There's different technical names for fire safety. So we call it fire engineering, fire protection engineering, or fire safety engineering. They all refer to the same thing. That is the science behind how we are making building or other structures safe from fire.
Laura, your background's a little different. So why are you interested in fire safety?
Yeah, you're right. My background is very different. Fire safety sits into the wider spectrum of just general safety science. And when I first started in the nuclear industry, a long, long time ago now, I did a lot of courses on how to make things safe, not just about radiation, but more generally what is called conventional safety. And all these courses started off with something that's a little bit like Anatomy of Disaster, which I think is a TV show.
I've only heard of Grey's Anatomy. I think that's a bit different.
Just a little bit, yeah. But all these things would start off with looking at a big industrial incident and the chain of events that led up to that, and kind of showed us that it was never just one thing that caused the incident, it was multiple things. Some of these incidents have led to changes in legislation. I mean, there was a Health and Safety at Work Act in 1974 that had big changes for how people did things. And these sorts of things sort of permeate through society as well. So an example of a really big event that I kind of remember learning about in primary school was the Fire of London in 1666, because we were taught the nursery rhyme that went with it. So all this safety stuff is it's part of our society and we don't really think about it that much. And I guess a really good example of it fairly recently was the 2020 Bahrain Formula One Grand Prix, where Roman Grosjean's car crashed in the very first lap and it burst into flames, this huge fireball. I'm not much of a Formula One watcher, but I was really shocked to see it. It was quite scary. The fireball was caused by a fuel system being damaged, but amazingly, Roman Grosjean got out of his car and walked out of this fireball. He had some burns to his hands and feet, and that was about it, which I thought was flipping impressive for all the engineering that went into that to keep him safe.
So this guy was literally in a ball of fire and all he had was a few burns on the back of his hands and feet and he walked out of it. That is insane. What makes things fireproof like in that incident?
Well, the first thing I learned about when I was doing fire safety training was about the fire triangle, which essentially says that you need three things to start a fire: oxygen, heat, and a fuel. To add to that slightly, the resultant reaction must be self-sustaining. And that's pretty widely known in the safety sphere.
I have personal experience of that from when I used to eat, not eat matches, but I used to put matches out in my mouth as a child because of the principles of the fire safety triangle. It's starved of oxygen. So when it's in your mouth, you've created a seal around it. The flame goes out and you don't get burnt. And your mum doesn't come at you with a cricket bat, as we've previously discussed. Go back to episode, I can't remember what episode it was.
It's the very first one where you fell out of a tree.
Yeah.
We were talking about risk.
Well, it's my favorite one.
So that's my personal experience of the fire triangle.
So did you know about the fire triangle when you were doing that with the match?
Of course. Yeah. I'm like, this is why it's being put out when I put it in my mouth. It's not getting oxygen and I'm not going to hurt myself. I use science in a controlled manner.
Science kept you safe. That knowledge kept you safe.
Definitely.
Yeah. So we talked about this oxygen there. I work with chemists quite a lot. I should point out right now that I am not a chemist myself. So I've picked up lots of chemistry terms from my colleagues over the years. They can probably explain this better than I can. But if there's oxygen there, then that suggests to me that fire is about oxidation. So it's a chemical process. And when I was reading up on this, loads of articles described this in terms of oxygen bonding to things that contain carbon and hydrogen, which are, of course, hydrocarbons. If you have some heat there as well, that provides the chemicals with enough energy to overcome some sort of thermodynamic energy barrier, I guess. And this then starts off the oxidation reaction. And the oxidation reaction is exothermic, which means it gives off heat. And hence that puts more heat into the reaction, so it becomes self-sustaining. So there's a little bit of chemistry behind why things can be set on fire.
Yeah, and I think that's so relevant because we've seen so many like forest fires these days. So about the reaction being self-sustaining and it keeps burning. Can it happen without oxygen being present? I know we said that, we have oxidation, but if there's no oxygen, can we still have combustion happening?
I think so, because another way of looking at oxidation from chemists again is redox reactions, so reduction oxidation. So oxidation is essentially loss of electrons, right?
Oil rig, oxidation is loss, reduction is gain. Is that right?
Yeah, I think so.
That is pretty much what went through my head when I slowed down to think about it. An example I saw on a few websites was a reaction between hydrogen and chlorine. So if these are sitting around quite happily, you'll normally have 2 chlorine atoms bonded to each other and 2 hydrogen atoms bonded to each other. And they get along fine. But if you put some energy in there, it creates this redox reaction. So one of them gives off electrons. First of all, they split into radicals. See, I've been around chemists for too long and I forget that there are some very weird terms in there.
I've not been around chemists for too long, so I'm having a intense learning experience right now.
Yeah, I'm trying to think how best to break this down when I'm so used to talking to chemists. And we all know what radicals are.
Of course.
But a radical is essentially, it's usually an atom or it could be fragment of a molecule. It's missing some electrons to make it whole, essentially. So that makes it really reactive. So if your chlorine molecules split apart into individual atoms and then missing electrons, that makes them more active, or there is an electron imbalance, I shall say. So obviously you can oxidize something, you can make it lose some electrons. There's a good example from the Royal Society of Chemistry where I think they expose a mixture of hydrogen and chlorine to light, and that causes it to have this really explosive combustion occurring, I think. It looks like a pretty cool experiment to me.
Thanks, Laura. So as we've already kind of discussed, if you remove one part of the fire triangle, that should make the chemical reaction stop and make the fire go out, as I have experience of with my matches. Is that always the case, or was I just very lucky?
I think so, yeah. So from my experience of a non-chemistry thing, thankfully I can stop talking about chemistry for a little bit. For example, if I'd been sitting around a barbecue and you're pretty much done cooking, but the coals are still there and it's quite nice to sit beside it because it's getting a bit chilly in the evening. And those coals are surrounded in like a layer of char. So if you kick the barbecue carefully, I shall point out, you can knock that layer of char off and it gets a lot warmer. So that reaction that is being prevented by the char forming, blocking the oxygen getting to it, then makes the reaction continue.
So that would be the optimum temperature for barbecue.
Without the char?
Yeah.
I guess so, yeah. I've never actually thought about barbecue temperatures. I feel like I should do some experiments now.
Leave a potato to bake on the charcoal. That's what we used to do, like on the leftover heat, just put loads of potatoes or vegetables and just leave them overnight. And then in the morning, they'd be really, really yummy. So we've talked a bit about the fire triangle and about how fires form. So now let's go on to the materials kind of things. What's the difference between a fireproof material and a fire-resistant material?
Fireproof material, it's a material that cannot be burned. And fire-resistant material is a material that would resist the heat for a certain amount of time, then start to fall off and be flammable. Then my experience as a fire safety structural engineer, what we're trying to do, because it's so expensive to have the material to be fully fireproof, we will make a requirement to make it fire resistant. Is basically to give the time to people to escape the building when it would start in flames. In this case, so like in building generally, if we think back to the fire triangle, you'll have the oxygen and you have the heat and you have the material. We can't live without the heat or the oxygen, can we?
We need to breathe, so we can't remove that from buildings.
We can't remove the oxygen and we need the heat, otherwise we'll freeze or not eat any cooked food.
I'm a fan of cooked food. I wouldn't want to get rid of that.
Essential heating as well.
The main thing we could modify to keep the building safe is the material. So is having the proper material the key thing to avoid a catastrophe. If we talk about something as simple as a cladding material, Do you think it would need a certain sort of requirement to be safe?
Yeah, there should be some kind of requirements for safe materials. I know hasn't always been the case, as we've seen a lot of buildings have caught fire. So I don't think it's always the case, but I assume there should be some kind of regulation.
Yeah, so if we take, for example, one of the grading material, aluminum composite panels made of thin aluminum layers with polyethylene, and polyethylene is a plastic. And if we don't get the right amount of material in there, it would become flammable because the plastic is flammable. And if it catches fire, it would transfer it, which leads us to something else. In structural fire safety engineering, we call it traveling fire. So the fire will travel from one bit of the building to the other bit of the building, and the media, or the mean in this case, will be the grading material. So the grading will transfer fire into bits of the material. So we would need to apply a specific regulation to keep these materials safe for the grading.
So this might be a silly question, but why was the cladding material made from something that was flammable? If you get oxygen in there, it seems like a bad idea.
Because of the cost and safety, and also the construction ability of the building. It is easy to use plastic to do that. It's very expensive to grade it all with aluminum. So if you got the amount of the material right, so like the certain thickness of the sheets and so on, it would be safe. It would be totally fine to use. But if for any reason you added a bit more plastic, it won't be. So that's why we have the regulation to specify what is safe and what is not safe, and it would be reviewed every now and then.
Seems quite like a fine balance. I know that there's so many buildings that have not suitable cladding at the moment, and that's a huge problem, isn't it, for people to change it? Okay, so we've discussed a bit about materials chemistry when it's come to buildings and the regulations. Now let's go back to the Formula One example that Laura gave about Grosjean. What made what he was wearing fireproof, and how did the change come about? Because I'm sure they've not always used such materials.
A lot of the fire engineering that relates to PPE started in about the 1960s, and it was in relation to racing cars. In modern Formula One stuff, they wear an inner body suit called Nomex that was developed by a company called, I think it's pronounced DuPont, but I might be wrong. I've only ever seen it written down. It's sort of a self-extinguishing fibre. And over that, Roman Grosjean was wearing a specially designed outer suit made by Alpine Stars. And all the suits the racing drivers wear, they've got proprietary technology in them that they won't talk about in a lot of detail to say exactly how they make them fireproof. That Alpine Star suit, it might have had air pockets in it that expand in the heat as they provide sort of a layer of insulation between you and the flames. So it gives you enough time to get out of that fireball.
Wow.
It's a very scary statement, actually, getting out of a fireball in time.
Yeah, it feels like something from a magic trick, isn't it?
I know, I guess if you understand the materials chemistry well enough, that's what it's like, right? So yeah, that Nomex suit that he was wearing, it's made from something that's called a meta-aramid that sounds like something out of the future, not something developed in the 1960s. It's essentially a semi-crystalline fiber, and the chemical structure of it is rings of carbon atoms, which are essentially benzene, which is highly flammable. So I find it a little bit weird in a way that it contributes to a flame-resistant suit. But I guess if you connect those benzene rings together, it changes the ignition temperature. And linking those benzene rings are some carbon, oxygen, nitrogen, hydrogen groups, which chemists will know as amide bonds. So that particular chemical structure means that it doesn't ignite in normal air. And it also stops burning as soon as you remove the heat, which suggests that there isn't a self-sustaining chemical reaction in that particular material. And that's what the DuPont website says. It's fire resistant because of the chemical structure.
That sounds like something from Star Wars movie that someone would wear not to burn in the atmosphere or something.
Yeah, it's very space age, and not continuing to burn once it's removed from a heat source meant that, well, I assume that even if it had caught fire while he was in that like wall of heat, as soon as he managed to walk out, that heat source is removed, and so it would stop burning. And I guess that contributed to him having such minor injuries considering the scale of the incident.
Yeah, the fibers transfer heat really slowly, and the weave's quite thick, so that would also help protect his skin and give him enough time to get out without getting too badly burnt. Yeah, I think the report said that he had burns on just his hands and feet. And I know that the gloves, I think I read something that was saying something about they were updating the regulations, and it was still coming through that a new technology would be put into the gloves that would give them a better heat transfer index, so it would protect his hands for longer.
Oh, so if they'd had the newer regulations, he may not have even had any burns on his hands with the new heat transfer index regulations. So it seems that Formula One has their own regulations that they stick to within their industry that the equipment has to meet. So going back to buildings, is there something similar in terms of heat transfer index regulations?
There is quite a lot of details on regulations, especially in the UK. So there's like 2 approved documents. So approved document A is to do with the structure and how to build it, the safety of that, the loading, and so on. There's approved document B, which is all about fire safety and fire resistant, because we can't really make it fireproof. It would be very expensive for a building to be a fireproof. So it would be a regulations and requirement that you must have in your building, so which make your building resist fire for a certain amount of time. So it would be an hour, 2 hours, and so on. And the more hours you add, the more money you would add to the project. So if you want your building to be safe for 3 hours, would be much more expensive than if you want your building to be safe for 1 hour, and so on. It's all detailed depending on what you're doing and what kind of construction it is in the approved documents.
It's making me think, do you have any examples in your own life where you can do things that you wouldn't expect you'd be able to do because of properties of materials?
I remember in chemistry labs in school, we had Bunsen burners on the desks. I don't know if they use them now or if they've gone to hot plates, because I presume hot plates are safer. I would wave my hand through the flame in the Bunsen burner.
I think that's worse than me eating matches.
But what I'd read was there's like a layer of air around your hands that protects you. It provides that insulation so you can wave your hand through fast enough and not get burned.
Do not try this at home.
Is that similar to putting off a candle?
I think so. Well, you're meant to wet your fingers when you do the candle, aren't you?
Yeah.
And you can definitely feel your fingers getting hotter if you do it with dry fingers.
And you have to do it fast, right? If you do it too slow, then you do burn yourself.
So is it the air that put off the fire, not your finger?
What, when you pinch a candle?
Yes.
Well, yeah, it's the fact that you stop the oxygen getting to the flame, right? That puts it out. But I think having the layer of water on your fingers provides you with some insulation whilst you do the pinching, because obviously that wick is still going to be hot.
You have to go with confidence.
Confidence in science. Yeah, that's what it was.
Oh gosh, we were terrible children. So I have a story of when I was a kid. So I was in Pakistan in the kitchen, and the gas is a bit temperamental sometimes. So I turned it up really high on the cooker because the flow was very, very low. And I had like a towel behind the cooker, and suddenly the gas came back and it was really strong and it was on high. And so the flame just, maybe it's called a traveling fire, as I've learned today. It traveled onto the towel, and the towel caught on fire. And me being like absolute disaster in panic situations, I just picked up the towel and just stood there like holding like this flaming towel. I don't know why I was doing this. I just stood there like holding it. And my auntie's just like looking at me like, what are you doing? And just grabbed the towel from me and just stood on it. So again, I think it's the same principle of like starving it of oxygen. So stamping on it works as well, rather than just water and things like that. So if you need to put a flaming tea towel out, standing on it, it works. Holding it doesn't work.
Waving it around through the air to give it more oxygen.
Yeah.
It's a flag of fire.
Flag of fire. That's what I was going for. So obviously there's several very like flammable materials. And I wondered, does anyone have any other examples of how you could fireproof? So how could I have fireproofed that tea towel so that it wouldn't catch fire when the gas kind of jumped in the supply?
In my undergraduate days, I did a lot of work with theatre. And the old theatre we were in, it was quite historic, and there was a lot of wooden structures in there. We were told that the theatre curtain that comes down across the stage, you can hold a blowtorch to it for 15 minutes and it will not set on fire.
What?
Yeah, which is quite impressive. I think that's to give enough time for, if there is a fire on stage, obviously you've got a lot of wood and you've got some really hot lights. It gives the audience enough time to evacuate, which I guess ties into building regulations to some extent, because you've got evacuation times to consider. But I was also on a committee that organised an end-of-year ball, and we had a lot of fabric as decorations, and we had to spray it in a compound that would make it fire resistant, which apparently is quite a standard thing, that any wall decoration has to be able to withstand fire. When I looked into this, some of the stuff we were using, it was some sort of like nitrogen-based compound with an aqueous polymeric binder, which sounds less futuristic than the Formula One racing suits. But I think there was something about when you apply heat to that, the nitrogen is released from this aqueous binder, and nitrogen starves the oxygen getting to the material, so it stops it from catching fire for a while, at least until the nitrogen is exhausted. And I also read that there are some fireproofing compounds that are sort of boron based and also contain a lot of water. And apparently, in an endothermic reaction, that's when the chemical absorbs heat, it releases water, and the rest of the compound then melts and coats whatever fibers you have in this boron, which, of course, if you're coating something with something, again, stops the oxygen from getting to it. So that prevents the oxidation. There are quite a few things out there that can make something that is flammable less flammable for long enough that you can get out of danger.
That's really cool. I didn't know that they could spray things to make them less flammable, but it kind of suggests that there's more to consider than just the type of material that we're using. Rwayda, given your background in civil engineering, what else needs to be considered?
So as Laura mentioned, you need a time to evacuate people. One other aspect is introduced now to the fire safety engineering, which is human behavior, because we need to understand how the human behave in fire. So like in your case, Aneeqa, you hold the towel and the other person who came in put the towel on the ground and stand off it. So that's an example of two different human behaviors. So in order to design the building to be safe and get the evacuation exit in the right positions, we need to understand how people behave. And the other thing we would need to understand is how the smoke travels, because the smoke is sneakier than the fire and even cause more death, because you will die from inhaling the smoke because there's no oxygen anymore because the fire ate that up. So we need to make sure that ventilation is right so the smoke won't be stuck in the building in the case of a fire. So there's lots of other aspects that we would need to consider regardless of the material is resisting fire and so on. Is how to get out of the building is a totally different story depending on the human behavior and fire as well.
Yeah, if you don't have a way to get out, then all the other things are a bit useless.
And I think some of my learned safety behavior, it comes not just from courses, but from, watching things on TV. There are lots of TV programs that will have a fire in some sort of disaster, and you're meant to get down on the floor, aren't you? And you see people doing this in the program, get down on the floor and get away from where the smoke is.
Unless you're Vin Diesel, and then you can walk through the fire without any injuries.
Because he's fireproof.
He is fireproof.
What's Vin Diesel made of?
But he's made of diesel. But according to Fast and Furious, he can walk through flames and make it out alive. You need to be made out of what Vin.
That's similar to the benzene thing that he used to do the suit, isn't it?
Yeah, maybe he sprayed himself in one of those fire-resistant compounds.
It sounds like that's a good place to leave it, because I could just start talking about Fast and Furious. I think we should draw the conversation to a close. It seems there's a lot of science and engineering that goes into making us safe. We've discussed some of the chemistry behind flammable materials and fire retardants. And we also heard about how regulations are constantly evolving to continue to improve safety. We don't see or experience most of these things, and it's all come about because of research development and historical events. Find us on Twitter at technicallysp11. What a catchy Twitter name, guys. Technically SP11, just so you remember that one, if you want to carry on this conversation or leave us a review, and we'll see you guys next time.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.